Okay, folks, how's everyone doing?
I'm pretty good.
Full down? Full down?
What's the question?
I don't know, you wanna full down?
75% off.
How is everyone feeling? Okay. I don't know if that's good or bad. It's always good, okay,
What
okay. So they get in your teeth, you know, you never know.
More popcorn. More popcorn. That's
Yeah. Okay, so first, bureaucracy. Oh no. What does that mean? You hate politics? We're not doing politics because this is a dictatorship, okay? So the first one here is that I have decided homeworks are now due every day. They're gonna be due Thursday. So why is this? Because it looks like people aren't starting them. Okay. So here's what I wanted to have happen. In my ideal world, you know, we talk about a problem, it gets assigned in class, and then you come to office hours right after and you say, oh, I understand the plan and we're gonna go from there and I'll do it on my own. And then if I have a question, I'll email you or I'll Slack you over the weekend as I do it. But I think in practice, what actually ends up happening is maybe you get done with the class and you're like, oh my God, that was annoying. And so you run away and you never look at it until it's the weekend and you're like, fuck. All right, now I don't have enough time and I'm stressed and I don't do enough. Does that seem reasonable to some people? Yeah. Okay, so to reflect that reality, we will drop them off on Thursday and that'll give you Wednesday and Tuesday's sessions to talk to me, okay? I still would really appreciate if you send me messages telling me that you don't understand something, okay? So it's a lot harder for me to know how the class is doing if everyone is turning in homework and there's no commentary on how it's going. No, you good? Okay, is that okay? Everyone okay with this new change?
Yeah.
Okay, is there anyone who cannot make either session, even though I asked everyone and I know people's schedules change as the semester goes on, you get a job, you take a different class? Is there anyone who cannot make either session? The health session. Okay, now the reason you're probably paying attention, are we doing a test or are we doing a check-in? So close your eyes. Close your eyes, everyone, close your eyes. Close your eyes, raise your hand if you would prefer a test.
That's,
Yeah,
so would it be like,
you can open your eyes again, sorry.
would we get like a cheat sheet at all, is it just? We get any type of.
You get the book,
You get the book,
yeah, you can have the book, it's open book, but it'll be in person,
open notes too, or just book?
just book.
But what if we only have the ebook?
I'll provide you a book,
Okay.
okay?
And then how long is it?
Full class.
Full class?
Full class, yeah.
How many questions do you think?
We could do 30 to 45 minutes, but I think arguably people would probably want more time, not less.
Yeah.
Right? Now, in the two different ideas, okay, in the check-in versus the test, you would still get a problem in both.
Yeah.
But in class, you don't have me looking right at your face and asking you questions. I realized, you know, maybe it takes me a little while to recognize this. I might be intimidating. I know that I try to be a friend, I try to be nice, but sometimes I might stare at you blankly and make you feel really bad about what you're asking. So I've done two things to try to combat this. One, there's more candy in my office. Okay, that's really important. If I can bribe you into coming to talk to me, I think you're gonna have better learning outcomes. Yeah.
We're funny sunglasses.
I have. What do you? I just bought brand new sunglasses. I also bought a brand new hat. That's why I have these funny lines on my head. Okay, that's not just how my skull looks. Okay. Whoa, thank you. That's so nice. You're very welcome. There's actually not even
Yeah.
No, I'm joking. Aaron told me that was free, so I wanted to make a joke. Okay, so that's the thing about the test. So some people might prefer a test. That's totally okay. Some people might prefer a check-in. In the check-in, we'll look at the work that you've already done. We'll comment on it, and I'll ask you a specific question that you will be expected to plan out. Whereas in class, you will be expected to do the whole problem. Okay, it'll be the same problem. Okay, and the final thing I'll say about this is instead of looking at the class as a whole, which is what I was going to do, look at your homework and say, oh, I think everyone needs this. I'm gonna let you choose. So for the folks who do a check-in, next Thursday will be no class. And you'll have to schedule some time, 30 minutes, one-on-one check-in, one problem. We talk about the entire class as a whole. And then for everyone else who prefers the test, you have to let me know before the class. And then you'll come in and I'll have that many tests ready.
Okay.
Okay? So your goal today is to tell me via Slack which you prefer.
Okay.
Anyone not on Slack?
How many questions will the test be?
At least one. Okay, test or check in by request. See, that's nice, right? Okay, now for this piece here. So I'm realizing when I'm looking at the homework that maybe what I thought was being clear about my expectation is not quite clear enough. Because there are some people who are not passing. Okay, and they are turning in the homework. So I want to make sure that I'm communicating my expectations well. Right, because of course we have a deadline, which is when I would expect you to turn the stuff in, but there's a little leniency. And as we talked about in the last semester, sometimes that leniency means like, oh, well, I'll just turn in half of my thoughts now, and I'll finish the other half of my thoughts. So let's think about the things that are important in the homework. And there's 4 categories. So what are the 4 categories of important things that I'm looking for in the homework? Okay, how would you characterize that? I mean, yes, that's right, but what am I actually grading for? Yeah.
I guess like justifying your choices.
Justifying your choices. Okay. And I'm going to say this a little more specifically at the outset. Oh God. Oh my God. Outset. What does this mean? This is making a plan. Okay. This is saying to me, look, there's spherical symmetry in this, and that means that Gauss's law is applicable here. And so therefore, I'm going to try to solve this dipole problem by solving one cylinder and then another and taking the difference. And then doing it. Okay, so what's that part? Algebra. Okay, everyone's least favorite part, but that's fine. Anything else? I said 4 things. There's obviously 2 more. There's 2 more that I thought of.
Equation?
That's part of algebra in my opinion.
That's fair.
Right.
Justifying if your answer is right. So another way of saying this would be like feedback or changes to the plan as you go. So as you get through, right, maybe you write some algebra and you're like, this piece here doesn't make any sense to me. I didn't like it, or I did this, but at this point here, it's an integral and I just plugged it into Wolfram alpha. I'm okay with you saying that, but I'm not okay with you not saying it. Does that make sense?
Yeah.
We're justifying why we make all the choices. And as we go through our plan, I need to see you engaging with that plan. So what I'm asking for is feedback. Feedback. Remember in computational, we do this whole thing at the end, like, does it make sense? Or like, how do I know the answer is right? You might get to the end and be like, I didn't really get it. Even though I did the problem, this is still really unclear to me. Do you mind going over this again? That helps me help you. Okay, so feedback and changes. Okay, and in particular, right, so this justification of your plan at the beginning, it can change. It's not set in stone, but you need to show that you knew what you were doing. Last piece. I love the enthusiasm, but no,
What your answer means?
that's kind of in here. A picture.
Oh, I see.
I'm seeing a lot of no pictures. And for me, if I'm seeing no picture, if I'm seeing no coordinate system, the problem that I have with that is then I don't know how you're orienting what your Z is. And I don't know when you do your little angle in a coordinate system that I don't agree with, if it's wrong, right? Okay, so we need to start off also by saying, okay, some choice of coordinate system. A drawing, a physical drawing of the situation. And finally, I'm just gonna throw this in here. This is not quite in the same bar, but some folks have really nice handwriting. Some folks use enough paper. I really like that. Some folks do not. Some folks take the entire problem and it's about this much on the page. And it's impossible for me to understand. Okay, so I'm gonna give you points for cleanliness. Okay. Make sense? So which of these is the most important? False.
Oh, shit. Oh.
False.
Feedback.
False.
that-
False. Okay, algebra is worth 40% of your homework grade. Because you need to be able to do it, right? If you can't do it, the class is worthless. Okay. Just dramatic part of my talking. Okay, what about this piece? Justification of the choices. 60%, nothing for these. Bold,
Yeah.
bold, okay, I'm gonna go with 30%. Because if you set up a bad plan, everything else is useless. So together with these two pieces, you can get a 70 in the class, right? You just do the algebra and you don't set up the plan, currently you have a 40. If you just set up the plan and you don't do any of the algebra because you don't have enough time, that's only 30. Okay, but if you do the justification and you make a picture,
45.
no.
Oh,
We're gonna go with 10% here for cleanliness, picture, and whatnot. And of course, if you can map, then you know what the last one is. 20, very good. Okay. So let's look at this now. Just algebra, no words, failing grade.
mhm.
Algebra and coordinate system, failing grade. Algebra and feedback, D. Algebra, feedback, and coordinate system, C. Algebra and justification, C. Algebra, justification, coordinate system, D.
Are you able to write what percent you think we have on our homework?
No, but you can look at it now. So as you look at your homework, just look at these pieces. Okay, I included algebra, good. Yeah. Just, I mean, and I give you feedback on the individual work, right? So I just want you to look at the work and remember, you can turn it back in. So if you have homework 1, which is all algebra, right? And no picture, you're like, oh, damn, I forgot the picture, right? Just draw the picture on it and give it back to me. Yeah.
Is there a limit to how much you can do that?
No. Every homework should come back 100%. Because I should get you to 100% understanding in the class. That's my goal. If I'm a good professor, everyone in here gets A's. Currently, we have F's. I do not want that to be the takeaway, right? Everyone with an F, I want to have an A, yeah.
Is it something like this last question? I would find it more helpful to figure out what I'm doing. Like, oh, your algebra is lacking. Just give me like a number for like where you are. Like this looks like a 60%.
Right, so this is what I kind of don't want to do. I understand your sentiment. And I'm not saying that that's not a good sentiment, but I want to deconstruct why we think about grades. Because in grades, I don't want it to be an impediment to improvement. So if I give you feedback to like, you know, this part of the algebra is right, or like you could use a little bit more words here, that should really be taken at face value. Which means that if you made that change, then I would believe that this homework was 100%. Does that make sense? So if something's missing, I'll say it specifically. right? And the absence of me saying something means, like, if you get no feedback on a piece of homework, and I just say good or right, that's good, that's 100%. Okay, I can't give you a second stamp, which is what I normally like to do, but now I give you a stamp for turning it in, so maybe I need a new smaller stamp, which says like hundo on the first try. And then you can like win stamps, which was my goal, or which was what we did in, which class did I do that in? We did stickers, right? Oh, I could do stickers, because those can't be removed. No, then you cut it out, you put it on another one with glue. No, I'm just kidding. Okay, so yes, I absolutely will give you feedback with regards to these, but I'm really trying not to put numbers. Because I think, you know, a lot of research has shown that once you see just a number, right, then it feels like you can just throw it away. You don't need to revisit it. Like, oh, it's 85. That's good enough, right? I want everyone to get to 100. And that's fine. You know, if you look at it and you say, well, I didn't draw a thing, that's like roughly 90. I'm okay with that. I'm okay with that too, right? If you're happy with your grade, you're happy with your grade. But I want you to make that informed consent, right? Okay. We all agree on this? Okay, I'm not gonna give you your homeworks back. One, because they're not here. They're downstairs. And two, because I got a migraine instead of being able to work last night. My brain turned off.
Okay.
It was really fun. I was like nauseous and I was, ugh, and I'm like, turned into dark and just listened to baseball. Okay. We are at the end of magnetostatics and matter. And this is a really fun time. So magnetostatics and matter has been sort of unusual. We've seen some parallels to, you know, E fields, and we've seen some parallels to B fields. And I think it will really help today, or at least I hope today, if we think long and hard about the abstraction, about what we're talking about on a grand scale. Because so far we have seen things like positive charges and negative charges. And then we have said things like things are magnetic, and that's kind of like, I don't really know what magnetism means. And now we think maybe we understand a little bit about what that means. But in practice, we are going to have some equations, Maxwell's equations, and we're going to be able to manipulate them in certain ways. And at the end of this semester, you will understand fundamental truths about the entire universe. Okay, so you start off with the stupid little wire and something coming off of it, and you're like, that's useless. And at the end, you understand how we can know how old the universe is, which is incredibly powerful, right? So in order to do this, I think, and maybe I'm wrong, you can say, Matteo, we don't want to review this. I think it will be helpful to review where we've gotten to conceptually. Is that okay? Because I was about to jump into this whole thing about V's and A's and potentials, and I was like, I think we just take one little step back. Now, in the V's and A's, we get to see my favorite symbol of all time, which is the D'Alembert. I know, we're gonna have some French today. But that's later, okay? Okay. All right. So let's first start. Okay. What is this thing here? Gauss's law. Very good. And what does it mean?
The spread of an electric field can be summed up by its charge density over the permittivity of free space.
Okay. Yeah, generally speaking, ignore this. You're reading, and I don't think that's wrong. But no, what I'm saying is you're reading it. You're reading the math, right? You're saying spread of E is the density over epsilon naught.
Yeah.
And that's not wrong, right? But if I were to explain this to my cousin, I would say that the reasons why we have E, the sources and sinks of E are charged, right? Because epsilon naught doesn't matter. If I set a world in which epsilon naught is 1, then all of a sudden this equals rho, doesn't it? Okay, these are just constants. All constants can be 1 if we decide numbers are fine. Does that make sense? Speed of light is like 1/2 of 1/3 of 1, right? You can just set c equal to 1. There's no real numbers in the world. Okay, so this first one, we mean that the sources or sinks of this weird thing called E is charge. Right? All right, what's this one? Oops. It's keeping you awake. All right, what's this one?
Every source needs to have a sink and a B field.
That is an interpretation. I do like that, because that would explain things like magnets, but that's not quite what I'm getting for. You're right that it's sources and sinks here, but the sources and sinks for B are 0. So this is the no magnetic monopole rule. There is no charge carrier for magnetism. Okay, this is not actually, doesn't have a name, but I call it the no magnetic monopole rule. So this says sources or sinks of B don't exist. Okay. Okay, in in electrostatics, this was true. What is that?
There's some spinny effects going on.
Swirly effect. Swirly, okay.
Swirly,
Swirly
sorry.
is a little different from spinny, and the
Yeah.
only reason that I'm gonna make this distinction is we may have seen in the homework, for example, that you can have, like, think about a fluid dynamic. You have something that is rotating, and if you have a drain, you can think about how the rotation changes, and you can get that to be curl free. So even though the whole thing is rotating, it's rotating in a way such that it has no curl. So it's really more like swirly than spinny. It's a small distinction, it's a wordy distinction, but you're right that saying, okay, here, there is no E, right, swirliness. But this is only true in which, what did I say? Electrostatic. So is this generally true?
No.
No, okay, this is wrong. Okay. So what is it instead?
Is it the change of the B field over time?
Correct. It's the minus change in B over time. Okay, and this was called Faraday's law. Okay, what does it mean?
And moving electric field causes a magnetic field. Changes magnetic field. Negative change.
Opposite of that. What's the opposite of that? Say it again, but say.
A change in the magnetic field causes a worldliness in the electric field.
Yes, okay, so what we're saying here is that a change in B field creates E. Okay? So here, dB/dt creates E. What's an example of this?
Electric generators.
Such as? Give like an example, like a physical object?
Yeah, I used to take apart TVs with them and they would have like the little like. Copper all rolled up around like a spinning magnet.
Yeah, so like an electromagnet, right?
Yeah.
Okay, or the another way to think about it is like, how do you generate power from a moving turbine? Right, like water goes over, rotates the magnets passing by each other, and as they pass by each other, they generate E. Okay, fair enough. All right, last one, del cross B. Does B have swirly swirl? Yeah, definitely swirly swirl, because this one said. No, no way to make B. So how to make B? J, very good.
Oh, yeah.
Oh god. Primes. Okay. How make J? How make J?
Current.
One.
Small current. There you go.
Things, charges moving. So moving charges make
Spinny bees. Or swirly bees.
any B. And only way to make B is J. Right? This is Ampere's law. Okay, so this one says that time changing B creates E. And this one says that time changing charge creates B. Reasonable or no? The charge moving, which is what current is, creates. Okay, are we good? No, we are not good. We are in danger. Okay, so this is the state of the art in like the late 1800s. So this is something to always remember when we think about how old the physics is that we were studying, okay? And we look at this and we say, this is really complicated and I don't understand any of it and I don't have an intuitive sense. So we're gonna begin to try to build an intuitive sense from physical properties. But in order to do that, we have to remember some of the way that vectors work together. Del cross dot of a vector is
Del cross dot.
del cross dot that vector.
Zero?
Yeah, it's 0.
Oh, okay.
Let me show you.
Sorry, I need to see it. Yeah.
It's a curl of it all.
Curl of a dot product is, but it's not just the dot product, it's the,
Divergence.
yes, the curl of the divergence is,
You're right, I would use it.
yes, that's why I'm erasing everything. Okay. Curl is this operator. Divergence is this operator. We're gonna find a new operator today, it's gonna be so sick. Okay, and then when we put them together, and this is just some arbitrary A, not something specific. So this is always
Zero.
Good. We're gonna use this. So that's why I wrote it. Okay. So let's have a look here. There's a little inconsistency. So del dot E is this, and del cross E is this. Right? So what if I take a dot product of this? Let's say I take the divergence of Faraday's law. And I would be writing del dot del cross E. And I apologize for not using the symbols here. You know where the vectors are, right? Did you say no?
Yeah.
Okay, I couldn't hear. All right. And so I can distribute this inside. And this says minus del T of del dot B. Okay, so this side is 0. And it's 0 because I just said it, right? Okay, good. So this thing is 0. What about this thing?
And that also is zero.
It has to be 0, right? Because this is the
Source of sensitivity.
right, no magnetic monopole rule. So this thing in here is 0, and the time rate of change of 0 is 0. Okay, so 0 equals 0. Awesome. All right, let's try something else. Let's try this one. Okay. So del dot del cross B is going to be equal to del dot mu naught J plus D. Right? So what's this?
0.
It has to be 0. Good. What's this? Assume that I do that properly.
It needs to also be 0.
Okay. Is it?
Or give balance. Or give instance.
What?
I don't think so.
I don't think so. There might be some circumstances where del dot J is 0, but generally speaking, this is not true. Because J is current. Right? And this would be saying that all sources of current are 0. No, that's not true. Right? We have current. I mean, the reason my phone works is because I have current. So I'm living on a day-to-day basis of knowing that current exists. So suddenly we have something that's 0 matched up with something that's not 0. generally. We're screwed, right?
Yeah.
Yeah, alright, let's go home. I'm kidding you. Let's stay there. Okay, so what is the clever solution? Okay. Let's add a term. Okay, so we need to add a term here that respects this piece, right? The del cross B, such that when we dot it, okay, this side minus the other side will equal 0. Okay. So we said something, or not we, I never said anything. So Maxwell comes along and he says, all right, what about this? What are the sources of charge? Sorry, what are the sources of current?
Yeah. What you said, charge.
All right, well, it's minus the change in rate of the charge, right? Okay.
Mhm.
Another way to say this is that if I look back over here, I can write this thing. You see this? As this thing. Right? So that means that I can take this and I can say minus the rate of change of, I believe it's epsilon naught, del, oh god, del E. Okay. Okay. All right, and so I can rearrange this, so this thing here, right?
Care about you not in all of these cases.
You're gonna see me not in 2 seconds. So here, what I'm gonna write is that del dot J, okay, is going to be this thing, and I can bring the epsilon naught outside. But this will be multiplied by this. So if I want to write what del cross B is, I have the term that I already know, which is over here, Ampere's law. And I'm just gonna add a term to it. So it's mu naught. There's J. I know that this thing here is this thing here, right? So I should subtract them. So I'm going to subtract this thing. Okay. Minus, subtract, plus. Epsilon naught. Okay. D E. Does that make sense? Sorry that it's off in the corner. Okay, so what I said here was, because I know that this right-hand side is generally not 0, I need to add a term to it such that when I add them together, they will equal 0 when I take the divergence. So here, right, no divergence. They're fine, they're coexisting, we're having a great life. If I take the divergence, then this side will unilaterally be 0. The del dot J will be this, which is minus of that. So I've constructed the solution such that I get 0. Okay, so this mathematical mumbo jumbo, is it meaningful? Is it helpful? What? Is it helpful? Is it meaningful? Okay. Specifically, it is helpful because we really need to look at what it says. So here I said del dot B, the swirliness of B is generated by currents. Now I've added a term. What does that term say in English?
A non-uniform change.
A non-uniform electric field?
Like it's changing.
Okay, remember uniform talks about spatial. The other word is time varying, right? So it's a time varying electric field. Gives you B. Okay, do we see the symmetry yet? Look here. If you can't, maybe I'll move this. If you're able to, view through the board. Oh, it's the cup, my bad. Ta-da. Okay, what does it say here? The swirliness is due to current and time-changing electric fields. What does that one say? The swirliness is due to time-changing magnetic fields. What about the current of magnetic charges? Okay, let's look at this, right? Let's look at the symmetry. dB/dt, this is the current, so this is the current of electric charges. So charges moving gives you J. And then if E is changing with time, gives you B. Here, E is generated by changing B, symmetry. What about the current of magnetic charges?
It's spin around.
Maybe they also. Wow.
Maybe they also, no. No, there are no magnetic charges, but if there were, they would be right here. Do you see the symmetry? So the current of magnetic charges, if they moved, if magnetic charges moved, there would be a magnetic current, but there is no magnetic current because there are no magnetic charges. So dt of 0 is 0, okay?
So it's like del cross B is 0 minus that because B doesn't have it.
Sorry, del cross B?
Del cross B is 0 to the.
Oh,
yeah,
del cross B, yeah.
okay. Got it.
Del dot B.
That's where the term is, if there was one.
Okay,
Got it.
so that is just where Maxwell got to.
Thanks.
Thanks, Maxwell. And he decided to call this this thing here. J, helpful, E. Okay, this is the displacement current. So you've heard about displacement field, and this is the displacement current. So this is the current generated from rate of change of E. And the canonical picture, the one that we like to think about when we make an example like this. I don't want to delete too much of this because we need some of it. Okay. Here's my perfectly drawn capacitor. Okay, two circular plates very close to one another, and I charge them up. Okay. And if I draw an Empyrean bag such that it encapsulates, one of the side, like think about a plastic bag and you like place it over one half such that this side is open to the wire and this side is completely in between the two. Okay. You'll find that if you don't account for the change in charge here, you will not be able to get the B field or the E field properly in this time changing system, right? So this is in detail. If you really care about this one, this is much better drawn, figure 743. And you've all seen figures 7. You've all remember reading this chapter, right?
Mhm.
I know I just talked to PK that you did this. Okay. Okay. So this is called Ampere's law with Maxwell's correction. We're gonna erase that entire board and we're gonna add it here. Plus and what are these called? All 4 of these? Maxwell's equations. Pretty cool. You just add one term and you get all 4 named after you. Oh no, he did more stuff. Okay. And we're gonna think about the more stuff that he did. So in the context of what we've been doing, right? We have this understanding now of where E fields come from and B fields come from. And these are like kind of tangible things. So let's think in context of putting this together. So like actual objects. Okay, so we're gonna start with the most primitive object. Okay, the easiest thing to understand in both your quantum mechanics class and this class, and that is
Point charge.
good. Yeah, no, that's right. Point charge. It's just so fast.
No, I thought you.
Okay, so point charge. So which charge do you want to use?
Somebody to choose.
Somebody to choose from, right? Hey, relax, please. Okay. Which charge do we want to use? Electrons, good. Say E minus. You say mid-choice. Okay, and so this generates what? An electric field. Okay, how?
Gotta have a plus.
Like it?
For E field, right?
Yeah, for electric field.
Yeah.
Magnetic field.
You like it?
Yeah.
Thank you, John. Come on, put your heart into it. Yeah. Okay. All right. Let's wake up. Let's wake up. Okay. Now let's do the next one. So I have E's. Now I need. No. So you have E minus. You need E plus, and that is
Stop.
a proton. Okay. I'm making this bigger because it has a physical size. E plus. All right. What does that look like?
No.
Do it.
But again.
I'm
I'm gonna do the hardest.
They're only going to get harder. So you do the easy ones now.
Let's go. Is it connected to this one or not?
No, just separate right now. We're gonna build the whole understanding of the class, and then we're gonna understand the inversions.
Yes.
What?
Wait, no.
Nice. Everyone like it?
Yeah.
There we go. Okay, good. All right. So this is at the beginning. Okay. So we have a proton and electron. And when they live together,
They interact together.
Oh, they make it electric dive.
when you add a proton and electron, you let them live in the same house. They're called
Attract.
hydrogen. Very good. Okay, so let's do. Okay, so now these are besties, E plus, E minus. They'll get really mad at me, so don't ever repeat this E plus, right? What are you supposed to use? Just P.
Oh, P.
But we're just gonna pretend, okay? Okay, so now they live together. What's the E field look like? For hydrogen.
Super net.
Oh, there we go. Let's go.
Guess it wrong.
I'm gonna get the direction wrong. That's what I know.
Okay, it's okay.
Just look at the top part. Don't overthink it. No, just don't overthink it.
Phone a friend.
Yeah.
Ask the audience. That's okay. We're not artists here. We're physicists.
They don't touch.
Look up.
Just look at
Fuck up.
all the arrows.
Okay, let's be nice. Let's be nice, okay? Yeah, very good.
Let's go.
Okay. All right. So in hydrogen, okay, we have some physical separation. And that physical separation means that there is a charge distribution between them. there is some ability to feel the field, right? When standing in between the electron and its proton friend, I'm gonna feel accelerated, right? One way or the other if I have charge. Okay. And so we constructed something. We saw that they had a separation. We saw that there was charge, and we called that a dipole. Okay. So we said there is a dipole, P. And we defined that as QD. Where Q is the absolute value of the charge and D is their separation. Good. Okay. So then we said, well, everything is like this, right? Everything's got protons and electrons and protons and electrons and protons and electrons. So everything probably has a little bit of dipole moment. And generally speaking, I add this stuff up, I add this stuff up, I add this stuff up. I'm going to end up with something that is able to be polarized. Okay. So we said, well, E, in the presence of anything with protons and electrons, is not really E. It's what? D, right? And we had some little equation, perhaps. So we're gonna write here that del dot D is rho F. What does that mean? What's that?
Row free charge.
The row of free charge. Good. So we're going to make a distinction in our lives. We're going to say the charge that is in the medium that is being polarized is different than the one that we would traditionally think of, let's say in our capacitor, our example of capacitor. We charge up on one side, we create free charge in a conductor, for example. You pump electrons from one direction, or we pump ions the other direction. That's the free charge. And it generates this thing called the displacement field. Okay. All right. Then we thought about this in more detail. We said, well, in practice, these things move. Right? That sucks. So now we have moving B. Okay. So where does magnetism come from? Well, let's think about our proton again. That's E plus here. Is he moving?
Yeah.
No.
Oh.
Remember, I confused everyone here because this is not a P. I'm writing E plus, and that means proton.
Oh, proton.
It's not the conventional sense. I'm just doing it to confuse you. I'm not doing it to confuse you. I'm doing it so that you think about them in terms of charge and not mass. But the mass of the proton is enormous compared to the mass of the electron. Okay. All right, and so now I have our good friend, and this is coming out in front and going behind. This is E minus. Does E minus have a size?
Well,
Nope. It's a real,
How does it have mass physics?
oh my goodness, you don't want to start. So you'll need to understand this class. You'll need to understand quantum. And then you'll need to understand what we call particle physics. Because our idea, our conception of mass is wholly inadequate to understand what things are at the subatomic scale. What I mean by that is mass is our ability to resist motion, right? I say that my ability to move this versus moving this, right? That has something to do with inertia. That's the Galilean mindset, right? But when we get into quantum mechanics and when we get into relativity, we'll realize that mass is energy. That should bother you. There's not enough of okay, everyone's heard of Einstein now. They don't think that that's cool. But the mass itself is rest mass. And as we start to accelerate a particle towards the speed of light, its mass increases. And it can never achieve the speed of light because its mass becomes infinite. There is a built-in stop in all of physics that stop you from accelerating to the speed of light, except if you have no mass.
Is its mass increasing or just the acceleration?
Both. The acceleration increases because the mass is going to infinity. So that's when we think about the total vector. So you think about, let's imagine velocity. So we think about it in terms of the velocity in this direction, the velocity in that direction, velocity in that direction, right? That's how we thought about it for all time. That's not right. We'll see when we think about special relativity that you have to add in a fourth dimension. This isn't a weird fourth dimension that you can't see. It's just that you need to consider time. Time is the fourth dimension. And similarly, we can construct what we call four vectors. What does that mean? That means that if I have momentum in this direction, and I have momentum in this direction, I have momentum in this direction, I need to consider a fourth thing, and that is energy. Okay, so you'll find that there are these correlated variables in special and general relativity that you need to consider both of them, because as you move towards the speed of light, moving very quickly, they begin to exchange in very unusual ways. So you may have seen something like this. Right?
Classic.
Classic. Okay. This here is the rest energy. Or the energy that a particle has with no speed. And the reality is that its total energy will include other terms. Okay? And this is the 0th order term. So the realization of Einstein was that materials that are moving very quickly, we normally measure those things on the right-hand side. Because that's you can't normally change atomic states, right? You don't just have like something in here which is converting these into the raw energy. That takes nuclear fusion. That stuff on the right-hand side is all we were measuring. But it's really, really small compared to the rest energy. Okay. So you might think I'm going off on a tangent, but I'm not. These three fields are deeply related and deeply important. Understanding how particles move, why they have charge, how they influence the world around us. You're getting to your point in your physics career where all of life's mysteries do this. So before you had like, you know, stuff moving on an inclined plane, and that was totally different from like a charged sphere. Like those aren't the same. They're all going to start to connect. And the place that we're headed to quite soon is trying to connect these two phenomena. One, which is associated with rubbing things on hair and then sticking them to like the roof, right? Static electricity versus like the way that we find our way in the woods, which is magnets, right? Compasses are magnets and they're attuned, and yet they're deeply related. And you'll see when you do particle physics, it's also related to the way that the internal structure of atoms work. Okay, so we're headed there. But first we have to understand this one. What's this one? Okay, E minus going around E. Okay, you've gone too far ahead of me, but I like it. So let's break this down. This is current. This is the idea of I, right? And because it's going around in a circle, that means that I can generate a magnetic field. Show me the magnetic field. You brought it up. No, you can't go again. No one can go again.
Yeah.
What do you want? Come on, folks. I don't want to sit here forever. I won't give up.
I won't give up.
I'll just talk about different stuff. No, I won't. It's very light. You think I'm that weak?
Right. Yeah, that's it.
There we go. Oh, let's go. That's okay. We're gonna guess together. Gonna guess together. Okay. So let's think about it in terms of the current. So let's go with our finger along the current, right?
Yeah, but is it like in the board?
Well, yeah, that's the question, where it's in the board.
Yeah, how did you draw, like 3D, like give me 3D.
Okay, so,
Right now.
okay, so here's I,
So like this,
right? So I is going around like this, and I've drawn it like this on the board. Okay, so you're drawing currently B outside, what about on inside?
it's,
You're so close.
Who's the outside?
Look, the outside one. You're getting warmer, like every line you drew, you're getting warmer. Now you're like burning up, you. Okay, wait a minute,
Yes, the outside.
go
Fix the
right
outside.
through.
Okay,
Target-
let's pause
target-
for a second, let's
yeah.
pause for a second, let's understand what's going on here. Okay, so we have a current loop, right? Here. So now you have your right hand, okay? Let's do current this way. Okay, now rotate so that you're in the direction of current, and these fingers will be the direction of B. So go,
so like this?
yes,
Going this way,
yeah, so now which way?
so is it going, can I receive?
Those are the
Those are
right
fine.
direction, but
Yeah.
which, up or down?
It's the wrong.
Sorry, they're in the wrong, they're the right Z,
They're the right.
they're the right plane, they're in the right plane.
They're in the, yeah. You got the right energy.
Yeah. That B.
Do we like that?
No, it's backwards. That's
I,
backwards.
yeah.
It is backwards, but we like it.
Yeah.
Okay, let's go, let's go.
As long as
The
it's,
arrows
as long
are
as,
opposite. on-
yeah. I was
So,
thinking
so
something else.
generally speaking, right, if we're doing the right hand rule like this, then it's up on the inside.
Oh, okay.
And then, right, so then you have to rotate
Down.
all the way around and then it'd be down on the outside.
just pretend,
But-
just pretend we're here.
Right, yeah, so I was just gonna flip that loop.
Yeah.
Okay, so now it's rotating.
You turn it around.
Yeah,
guys.
don't
Turn it
worry about
around right now.
Ta-da! Okay, but this is the idea.
Yeah.
Right? Moving electric fields generate magnetic, sorry, moving electric charges.
Yeah.
Okay, moving electric charges generate magnetic fields. Okay, so this is what we found. Right? They're living together, they're having their best life, and they're making this stuff. Okay. And then we created a new thing. We said, this is M. What's M? Yeah, kind of. M is the,
Oh, big N?
let's call that little m,
Oh, okay. Magnetic dipole.
the magnetic dipole. Okay, so now this is the ability for a material to be rotated because there is a dipolar nature, right? Or, okay, can be moved too, but in general, we're talking about rotation. Right? And what is the cause of this? I've given you one of them, but in fact, there are 3 types of magnetism. Para, dia, ferro. Okay. Are there 3 types of electricity? No. There's only one type of electricity. Okay. This one comes from? What? Yeah, that's the direction, but what is it, how is it generated?
Oh, one spin and one something,
One spin and one's
something.
orbits.
Yeah.
So we just drew an example of an orbit, right? And what we need to remember here is this pretty picture that we've developed only explains one of our 3. You see? So generally speaking, we can use this idea if we want, but it won't always be sufficient to understand how B is generated because it can be generated from unpaired spins of the electron. That's a form of moving charge. Okay, even though it's not really spinning. It's a headache, I know. Okay, so in general, we think about these 3 as simply existing. And they gave us our favorite thing in all of science, which is H. L cross H. And what's H again?
A weird magnetic.
Yeah, it's just magnetic field. It's also magnetic field. Magnetic field is magnetic field. Some people call it auxiliary field. Some people call it the magnetic flux incidence. Who cares, right? It's just also B.
Yeah.
Right? It's the thing that we measure in the lab. It's the real life B. Right? So if I'm looking at in space and I'm taking observations of the way that different materials interact with each other in space, then I'm probably measuring B. But if I'm in my day-to-day, it's B.
Yeah.
It's H. Okay. Okay, and why the cause of this?
Is it the free charge due to the magnetism?
Free current.
Free current.
Free current, love it. Okay, so we call this JF, right? So we're using some of the similar reasoning here. We say, well, material is all made of these ions and electrons, so all of them have an inherent magnetizability. Wood is magnetizable. I'm certainly magnetizable, right? I wouldn't like it, but it would happen. Right, the water in my body is prepolar, and there's a bunch of electrons in there, and like they're all moving around. So you could have a magnetic dipole moment. Probably wouldn't be very good.
Probably not.
Okay, so you have some free current in real life.
That what MRI machines do?
No,
Yeah.
no. Those use nuclear spin flips to look where certain atoms and ions are in your body.
Okay.
Yeah, we won't hit that in this class. You would hit that in a particle physics class.
Okay,
You might hit it in modern physics. You think modern?
Yeah, we did.
Yeah, magnetoresonance imaging, you would talk about it a little bit there. But if you're interested, I have a fun book that I'll lend you, which just like talks about like the discovery of subatomic particles. Like, oh, we can use this to like peer inside of humans. Pretty cool. Okay, are we done? Don't say yes.
With this equation,
Are we done with this equation?
I guess, is there a view top or something on this?
okay, yeah,
What?
now we can kind of, we can relate those two, maybe?
Oh, yeah. This is where I started today, right?
Yeah,
It'd be the D, right? So this piece here gets absorbed into our definition of H, because H and B are related by this little jibbity jab. And then D and E are related by this jibbity jab. So in fact, we can just write
nice.
yeah, beautiful. Who's symmetry? Okay,
Skipping symmetry.
something like that. Okay. So that is where we stand. That is the state of the art of what we know, right? We think about this in the context of potentials. I haven't written a single potential on the board. I haven't talked about potentials. We don't even know that they exist yet, right? We're just talking about real things that we understand. But we can think of potentials because they help us to connect these in ways that aren't quite obvious yet. Are you ready for that? Okay. I'm also not gonna be able to finish this today, that's fine. But what are the rules about potentials? We understand potentials because we think about this mostly in the context of, oh, something will do that. So if I look at a hill, I can see the potential energy. I climb up the hill, I think about a ball rolling down. There is stored energy at the top of the hill that can be released by the object coming down that. You're observing gravitational potential energy. Okay. So this is the first rule. E is generated by the gradient of V, and in particular, the negative gradient of V.
Yeah.
Okay. Is this true for the B field? Why not?
I think the B field.
Yeah.
So let's try that out, right? So if we had that, we tried it over here.
We have a curl, between.
You'd have del cross B dot A. That would be
Oh.
0 on this side.
Okay.
Alright, that wouldn't be the case on this side. So generally speaking, we write this. Del cross A.
Oh.
And we said that this one was great. We like this one. Like this one? Oh my. You said it's okay?
It's okay, yes.
I don't like it. I don't like it because it's non-unique. And it's really annoying. But there is some benefits. No, okay. So generally speaking, let's see what happens when we write, say, something like B in terms of A. Okay. So let's take this first one and let's take, you saw this in the end of last class. E plus del A del 2 equals. You remember that, the end of last class? This piece. This piece. Moved it over. Rearrange. Got that. Okay. Okay, so you can also say that E is equal to minus del V minus dA dt. Well, that's funny. How do I get there?
So funny.
Let's rearrange it. So funny. Oh my god, so witty. Okay, so this says the same piece that we said before. That there is a gradient of the potential, the electric potential. That gives us the electric field. But now it includes in electrodynamics changes in the potential, the magnetic potential. Right? Which is kind of what we talked about here. We're saying the same thing 2 different ways. But now I have a way to solve E with a time varying A and B. Okay. All right, one more piece here. If I take del squared V plus d dt. Oh god. Del dot A. Okay. This is minus rho epsilon naught. How did I do that? Hogwash, right? Yeah. Okay. All I did was I took del of this entire equation. Okay, del dot. Oops. And I went to here. So del dot E is rho over epsilon naught. Del dot del is del squared. Del dot dt is this. You see that?
It looks similar to like the continuity equation.
Okay. Similar to the continuity equation, I like looking for similarities here, but in fact, this is where we get our funnest symbol of the day. Okay, can I get rid of this?
Wait, Chris, what?
Yeah.
Why did those two become positive?
I just moved the negative over.
Oh,
Remember, that's not the negative here.
oh,
I just moved, yeah, so it's negative, negative, and then for just me not writing a bunch of negatives. Okay. This is enough space. So let's say we want to find an equation for J. Okay. We can start with del cross B, which becomes del cross A. Ugh, that's gross. And we can do some rearranging. Okay, and what you'll end up with, I promise you, not a joke, real thing. Okay, I know that's not a good joke, but it's for real. So that's A. okay, minus del dot A plus mu naught epsilon naught del V equals minus mu J. Got it. Okay, that looks horrible, right? Does it look bad?
Yeah.
Does it look okay? You understand it intuitively? No. Alright. Well, first, this is the del inversion.
Yeah, one more time.
This is the del inversion.
In a lens version.
Yes, this is a big rectangle. You can draw it as a rectangle in your notes because that is the symbol. It's the coolest symbol in math, and if you disagree with me, you're wrong. So here is the del inversion. And the reason why we like the del inversion is because it takes the gradient and it combines it with time variation. Right? 2 time derivatives, a bunch of space derivatives. Question?
Is there always a split? On the rectangle?
Oh.
Oh, in the del inversion? Yeah,
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 sorry.
yeah. On the rectangle? How dare you? Okay, if you want it for your notes, it's called. Okay.
All right.
What?
I told you that we were doing French today. Okay, del inversion.
I thought like Del,
Like,
Del.
Like Del,
no,
like Del Taco, Del Inverso? No, okay,
it's,
what's that? Yes, it's French, not Japanese. All right. So, we can rearrange a little bit of this. I mean, I could write this up, but I don't think we have time. Except to say that this is ugly, right? But this is not that ugly. And I'll argue why that's not that ugly when we begin to study these things called waves. So if you recall from fluid dynamics, there's, don't shake your head that you don't remember fluid dynamics. It's gonna hurt my soul in ways that are irreparable. Okay, so there was different ways for waves to move. Okay, we would notice that they would move in time, right, from left to right, traveling waves, or they might move up and down and appear like they were moving either way, right? Standing waves that don't move up and down, that just move in space. Moving in space, moving in time. These here, solutions to this object are waves. So what I'm trying to get to here is that you have a current which is generated by something very ugly and something that might be waves in the magnetic vector potential. Okay, so it looks like we started with 4 equations plus some other ones, but what we're doing is we're trying to piece these things together, the sources of charge and the sources of current, to these potentials so that they can be used interchangeably.
Are we gonna end up with like complex numbers?
Not just complex numbers. Before I continue, I'm gonna leave this del inversion here, so that's the ripest thing in your mind. The coolest thing you've learned today is the del inversion. But you will need to start, especially for next week, look at chapter 8. Chapter 8 is where we're going, and then we will do waves, and then we will get into radiation. And so I'll put this up on the calendar. As we noted at the beginning, homeworks are now due Thursday. Indicate to me whether or not you want to do a test or a check-in. And you should be using the new homework grading to look at your own work and determine whether or not you're failing. Yeah. Did you have a question?
Yeah.
Okay, no worries.
Do we have homework to do next week?
Yes, of course.
Wait, so
We will never not have a homework unless, probably when I'm in Tokyo, you want to. That's not till November.
So this one we're doing next Thursday instead of. During the whole 4, right?
We'll do Thursday. We just turned in.
You just turned in 3 and you're gonna turn in 4
Thursday next week.
next Thursday.
Okay, okay.
Not today.
Where's my homework?
Do you have a question now?
No, I just like the Thursday.
And that is to encourage you to go to office hours. And in particular, when you don't understand something, communicate to me earlier rather than later. I don't mind seeing on your paper, hey, didn't get this, don't know how to go on from here. That is more instructive to me and I'm more able to help you than if you turn in something that you don't really get because you were worried that you didn't turn anything in. Right? Because if I get a homework from every single one of you and it's all done, but 20 or 30% of you don't know what it says, then how can I address that as a professor, right? I don't want to fail anyone. Okay?
If you want to deal.
No, that's false, John.
I need to take off.